Okay, before we start the session, a couple of announcements. There were a few people that registered to the dinner after closure, so during the registrations. That's fine, so you can come to the dinner and you will have to pay at the restaurant tonight directly. Another announcement, so for the speakers, I invite you to try to stay on time, otherwise we miss the bus tonight. And I will tell you how much time you have. In this case, Gian-Luca, you have 20 minutes plus 10 of questions. And for you that are doing the questions, please speak very close to the microphone. Thank you.
Okay, perfect. So, can you hear me? Is it okay? Okay, thank you. So, good morning, everyone, and thank you for. Sorry, I was too early.
So, welcome to the algorithm implementation session. The first speaker of today is Gian-Luca Brazerol. Gian-Luca graduated in 2023 with a bachelor in electrical and computer engineering. During his bachelor thesis, he was first introduced to FPGA-based time-to-digital converters, where he implemented a wave union TDC. Since then, he has been working part-time as a research engineer at the Institute for Microelectronics, Embedded Systems and Sensors at the EOST. In this role, he continued to work on TDC projects and is currently pursuing a master's degree in electrical computer engineering with a focus on microelectronics, specifically analog IC design.
Okay, thank you, Davide, for your kind introduction, and good morning, everyone. In this talk, I want to talk about some aspects on linearity and temperature dependency in FPGAs, specifically for time to digital converters. For those of you who don't know, time to digital converters are basically very precise stopwatches where we have or achieve time resolutions in the order of a few picoseconds. And as a matter of fact, I will start my own stopwatch now and set it to 1.5 quadrillion picoseconds, so to keep my presentation time a bit in check. Now moving on, I will first make a short introduction so we all know what I'm talking about, and then dive deeper into some considerations for linearity and temperature stability. I will make an overview, performance overview for different FPGA vendors, and conclude with a sort of a guideline, which FPGA to choose when you start your own TDC project. But first, we need a motivation. Why do we put so much effort into this? Well, certain applications require very fine timing resolution. The most famous would be a time-of-flight application, LiDAR, where we typically want to measure distances. And you could try something like this, which is a synchronous ripple counter. But assuming you could clock this with 1 gigahertz, your LSB would correspond to 1 nanoseconds, which gives you a distance of 15 centimeters. So if you want to map a room with a scanner, this is not really sufficient. Another field of applications come from time-resolved biomedical imaging. FLIM, for example, where you excite a biological sample with a laser and measure the time for the sample to emit a photon. And with this, medical staff can get some insights. Please don't ask me too detailed question about that. I don't know anything. We just count the photons, measure the time, and they're happy, so we're happy too. And of course, you can play around with these time-to-digital converters. For example, you could implement a ramp ADC in an FPGA only with parasitic capacitance of an I/O pad. And as these synchronous solutions do not work, we need something else. And people came up with an asynchronous approach where we exploit the hardware of FPGAs And in modern FPGAs, fast carry logic is well established and used for fast signal propagation, and thus they make an ideal block for these delay elements, so we get fine resolutions. And with this example from a Xilinx UltraScale Plus, a carry 8 element, I want to show you how you characterize or what performance measures are important for a TDC. Well, first, we use these multiplexers within this carry chain as delay elements and sample these, or the state of the carry chain using the adjacent flip-flops in this slice. And I will refer to the sampled outputs as bins for the continuation of this presentation. And the signal will propagate like this through the carry chain, nice animation. And now to the performance measurements or measures. The first would be the measuring range, which is the sum, in this example, is the sum of all the propagation delays of these multiplexers. Now, of course, this wouldn't be a very huge measuring range. So in reality, you cascade multiple of these elements to cover an entire clock period. And then you can further extend the range with a synchronous clock counter. And the overall solution would then be the combination of these two results. The LSB, in this case, is the mean propagation delay of these multiplexers. It does not represent the actual propagation delay. These, in reality, differ from element to element. This is not what the LSB says. We have a dead time. This indicates your blind spot where you can't measure anything. For example, here, this would be the minimum distance between two edges to correctly distinguish them. Ideally, this would just be one bit, so one element, but we have a so-called bubble effect, where in the sampled pattern are irregularities, so you don't have clear 0 to 1 transitions, so the edges are smeared out. And this mainly comes from non-uniform clock skew of the sampling flip-flops and routing. And as we violate setup times for the flip-flops, metastability can also cause these bubbles. We have the nonlinearity measures. In this picture, for example, you see that the distance the signal has to cover is not uniform and differs for element to element. And with the differential nonlinearity and integral nonlinearity, we can characterize that, but I will come to them later. And you have your precision. This is greatly influenced by your ENL and the clock jitter. And yeah. Was there something else? I think I got it all. Of course, you could implement such a setup in a custom silicon. And you could fine-tune all the clock skew and all the clock network and all the path delays so that they're uniform. So there would be a benefit or an advantage in linearity, but development cost and development time would increase. What was it, 16 nanometer MPV from TSMC costs you around 60K for 1 square millimeter, while an Efinix titanium runs at about $70 and is in the same technology. And of course, the typical pros and cons apply here too. But now to linearity. We can measure, when we construct such a tapped delay line, is what we call cascadation of these carry elements. And we can measure the actual propagation delay of every element. And we do this by feeding a periodic signal into this carry chain, where the frequency is uncorrelated with the sampling clock. So each bin should be hit evenly if we have an ideal TDC, but yet it doesn't. And if we look at it, this histogram, we can clearly see this very, very big peak in the center. So there must be a huge delay in the middle. Now, why is that? If we look This is for the ultra-scale plus, of course. If we look at this figure here, we can see here that this is one clock region where we placed this carry chain, and here right at the middle, the top here is cut off, are all the clock buffers are located, and the clock is fed into this clock region and distributed from there to the sides. Now our signal that we send into this runs from bottom to top, and in the middle the clock changes direction. So this results in this huge bin we see here in the center. And this could also apply for clock region crossings. The effect, or the degree of how the effect comes into play depends from FPGA family differently. We made the experience with the 7 series Funkzilings, where you have a larger bin at the clock region crossing and not in the center. So you must test out what works for you. Now, for the rest, we can see that the other larger bins seem somewhat periodic, and if we zoom in, that is really the case. The distance is exactly 16. Now, the question is why? And it is because we cheated a bit, well, except for only using these flip-flops here that are depicted here. We can also use this carry-out signal after every multiplexer. And there is also an additional flip-flop in the same slice. So we get 16 bins per such a carry-8 element. So in order to avoid such huge bins, you must place your carry chain very carefully. What effect this has we can better see here in these plots. These are the nonlinearity figures, the differential nonlinearity and the integral nonlinearity. The differential nonlinearity tells you for each bin how much it deviates from the mean, so from your LSB, which I plotted here in red, while the ENL is the accumulation of the DNL, and it tells you the absolute time difference for every bin that you have if you compare it to an ideal TDC and you would not calibrate it. So, and as you can see, this huge bin has the effect that here is a really great jump. And if we look at this, we are at approximately 25 LSB with roughly 2 picoseconds as an LSB, so we are 50 picoseconds off. But you can calibrate it using this ENL and correct it. This is better explained here in reference 9. I appended it, calibration methods for TDCs, where it's very well explained how you do that. So I don't want to go further into this. And here is another example of this, but this time for a titanium, Efinix titanium FPGA. On the left, we randomly placed our carry chain and characterized it, and obviously here we crossed a clock boundary, resulting in this huge bin. And after we replaced our carry chain within the same device, but we replaced it. Oh, now I got too excited. We can see that it's we don't have any of these huge bins and are very, very linear and stay almost within ±1 LSB, which is very good in general. But it does not stop there. The takeaway is you must carefully, or you must know where you want to place your carry chain in order to get the maximum out of your performance. And this is individual. If you have multiple carry chains within the same device, for every single delay line, because they behave differently, you need you have to characterize it and you have to calibrate it with the ENL. And once you found a good position, it doesn't stop there, because from die to die, this changes. We tested 5 different Arctic 7 FPGAs with the same bit stream and characterized the carry chain. And it is not only the difference in length, which in this case was 15% difference, but it's also the pattern that behaves. But, well, as you can see, the plots look very similar, so there must be some systematic process behind this. It makes sense because they're the same chips, essentially. But this also highlights that your calibration scheme must cover these eventualities, and that it must be robust enough and individual for each delay line. As you can imagine, such a setup is very prone to temperature changes. And here we measured this for 5 different FPGA families. And we measured how many elements do we need to cover a single clock period, which is different, of course, for every FPGA. And, well, you can calibrate it, so it's not a real problem, but the changes are, especially for the Intel FPGAs, is quite larger than for the others. We don't know what the underlying structure is, so if the designers incorporated some sort of temperature correction. And it's also individual for every delay line. So again, you have to calibrate them individually. And it's sometimes counterintuitive, because from my perspective, the warmer it gets, the slower your FPGA becomes, but this is not always the case. For example, the ARIA 10 or the Arctic 7, for some reason. We don't know. But we have people here who design these things, so maybe we can ask them what it is all about. This is an overview from all the corner values for the 5 dies we tested, or FPGAs we tested. And this is for all temperatures we measured, so from minus 20 degrees to 80. And we can see that there is some sort of tendency that if we have a very low LSB, like this Ultrascale Plus and both Intel FPGAs, that the lower the LSB, the higher your nonlinearity figure gets. While if you have a larger LSB, for example, the titanium or the Arctic 7, you tend to be very good, or rather good in linearity. And this is strangely independent from your technology node. If you compare the Ultrascale Plus and the titanium FPGA from Efinix, there is quite a difference in your performance measures, which we can explain to some degree the linearity, but not the LSB. If you have a look at the architecture, you can see that in the Ultrascale Plus we have 8 outputs that are reasonably close together, and then one huge bin. This results in bad or worse linearity, while the Efinix FPGA has just a single adder per logic slice and then moves on to the next. So we can expect a more uniform linearity. Why it has such a huge LSB, it's not really a problem. It's very stable. We don't know. We need to ask them why this. What both do quite well is that they place the sampling flip-flops within the same logic slice, so you don't have to cross any slice boundaries, which would add new uncertainties. Now, to the conclusion, we were able to implement in all the devices a functioning TDC to evaluate this data for this presentation. We were successful for all of them. I personally think with enough effort, we could implement similarly good TDCs in every device. But I think depending on your requirements, you can choose the right die and then save a lot of development time. Yeah, but it's also a bit of a personal preference what you want. What you need to have is a deep understanding of your low-level architecture. This is essential. Well, you need to place your TDL very precisely to improve your linearity performance. And again, each TDL requires its own calibration to get the maximum out of your TDC. I have one last remark. If you are a FPGA designer or vendor and you think, oh, this is cool, we would like to get our FPGA tested, you can send your development kit to us. This is the address. Preferably, it has a FMC connector. I also would like to thank Safran Vectronics from Herbrook. They did not sponsor this presentation or this work, but over the years, with their projects, we gained a lot of experience and got comfortable with this topic. And without these projects, we would not be able to get all this work done in this short amount of time. And that's it. Thank you for your attention. Do you have questions?
Thank you, Gian-Luca. Questions?
Hi. Thank you for the great talk. I have a question about the code that you wrote for these tests. Were you able to write generic code to infer this functionality, like in VHDL, or did you have to use primitives from each device family that you targeted for each test?
Yes, great question. Thank you. Yes, we actually used the individual primitives from the FPGA vendors. It's because we manually place these elements so that the tool synthesizes and places it just there where we want. So we did not implicitly describe this behavior. We explicitly instantiated these primitives, yes.
Thank you.
Hello. I was wondering, you're not only picky to temperature and process, you're as well picky to the core voltage. Did you try to modify the core voltage slightly, very, very slightly, and see what you get then?
That is also a very good question. We didn't investigate that, but of course, if you would play around with the supply voltage, well, I would expect that the behavior is very different. So, yes, well, it's generally a good idea if you calibrate your TDL or your TDC from time to time to get rid of such effects where you have temperature variation or supply voltage variation where the behavior changes. We didn't investigate it here, but it would be interesting, of course. Development boards don't usually allow that, and we work a lot with such boards. So, yes, but thank you.
I have no microphone here. Maybe I can ask. Which kind of TDC did you implement? It's just a simple delay line TDC, or it's like a wave union or something? Okay. So I ask if it's a wave union or something that make average with multiple runs of the wave inside the TDC, or it's just a simple TDC? And sorry, second question, it's the code available on GitHub, I don't know, somewhere to look at your implementation?
Yes, for the first question, no, this is just a simple tap delay line we used for this work. It was just a very, very rudimentary TDC with just a delay line, and we made sure that the pulses are far distant enough to just count the number of ones we have, and thus produce the histogram. Of course, you could implement modifications like a wave union TDC. We have already done this, but not for here, but you could, of course, which would improve your performance, or your LSB, of course. And to the second question, the code is not publicly available on GitHub, but I think I have to, well, we have to discuss it, and maybe we can provide it. The code we used here, probably I would say should be possible because we didn't do it with any industrial partner. So I think this should not be a problem.
Thank you. Thank you very much.
Hi. Have you broken down on slide 7 the variations on the individual flops that you have? Like you have 8 flops in a CLB, right? Like A, B, C, D, and so forth. And the difference also varies a little bit. So is there, you have something like a systematic changes, and you have also process variation changes. Have you differentiated between those?
Sorry, could you please repeat? Sorry.
Your carry chain is somehow physically implemented out of 8 flops in a single CLB, okay? Yes. And there is a systematic non-linearity between the 8 bits, and there is one that is depending on process variation. And you can differentiate between the two. Have you done that?
No, I haven't.
Okay.
I would need to look into that. I think maybe you could break it down, but it should be in this or included in this, not?
Yeah, this is specifically interesting for Xilinx Ultrascale because your carry chain is actually, or can be used as a carry look ahead adder, which is ridiculously fast. Mm-hmm. And then you get some very weird effects. Okay, then. For the long distance, your carry chains, rather than breaking into another effect. Oh, technology. For the long distance delay chains, rather than breaking into another clock region, you may want to have multiple parallel chains side by side connected to the same clock, so you have less impact by clock jitter, and you have an initial delay how you feed in the next TDC. That gives you overall better accuracy.
Mm-hmm. Yeah, we haven't done that. This is a very simple implementation, but of course you could place multiple TDLs to improve your performance. And what you mentioned is the clock region crossings. Of course, you should make sure that it stays within these boundaries, so your sampling clock should be sufficiently fast.
The problem is if you go in another clock region, you have a different, let's say, clock routing to get into that region,
yes,
and then you get some jitter in that you don't get in if you have dependent, let's say, clock variations, which you have if you stay within the same clock region. Mm-hmm. So there's a good reason to do that one.
So you mean you would place 2 different carry chains in different clock regions to cancel out the jitter?
Exactly not. You want to have them side by side connected to the same clock tree. That's important.
Yes, so this is a possibility. Is it what you mean? I don't, sorry.
One last, I have a few more things, but one last thing. You mentioned the different speeds of different FPGAs.
Yes.
Have you just tried to get the fastest speed grade? Because then Xilinx or Altera or whoever would have done the speed binning for you already.
Yes. We haven't... it was a discussion, what impact does the speed grade have of FPGAs? And well, the way that devices are characterized is they do some tests, and then whether they pass or not, they divide them in different speed categories. And from my understanding, it is if you have the lowest speed grade of a device, it failed some tests, but the individual carry chain could also be fast, just as fast as in the fastest speed grade. You could get lucky. We made this experience. It's not that everything is slower. It failed some tests, and thus it is characterized to a lower speed grade. But I would say that maybe if you would place many carry chains within this slow rated device, you would get very different behavior for the carry chains. And if it would be a fast rated device, the differences might be more uniform. This is what I would understand.
Maybe we can continue this discussion offline
Yes,
in the coffee break. Thank you, Gian-Luca. Let's thank him again. So the next presentation